In addition to needing the metric system when we're working in a science lab, we also need to worry about something that we refer to as significant figures. Significant figures are a way that we show accuracy within our measurements. Different measuring devices have very different levels of accuracy. And it can be hard to express that in a number. So it's our significant figures that will let us show how accurate our measurement is. So let's say we're in the lab measuring out a liquid, and this is our graduated cylinder. And we'll say that is 1 milliliter, and that next mark is 2 milliliters. We then fill it up with whatever we decide to fill it up with. And we can clearly see that our measurement here, if we're going to record that, it's not 1 milliliter because we can see it's quite a ways above 1 milliliter. We also know it's not 2 milliliters. And we know that because we can see that it's well below the line for 2 milliliters. So how do we record this measurement? So as we said, our measurement is limited by the accuracy of the device that we're using. So we know this is going to be between 1 and 2. And if we look carefully, we can see that the liquid there, it's definitely more than halfway. And so maybe we guess that it's approximately 1.7 milliliters. What we're saying here is this every digit before the last one, we're very certain of. We can see based on the graduations, the markings that are on our measuring device, that we know that that one is accurate. But because this measuring device only gives us to the nearest one, we then would need to guess, or estimate would be a better word, one digit further beyond what our measuring device shows. So again, because this measuring device shows us to the nearest one, we're going to estimate the tenths place. And so that last digit is going to show our uncertainty. Because we might, someone else might look at this and say, I think that's closer to 1.6 milliliters. Again, we're not sure of that final digit, and that's how we'll make our interpretation. Now, which digit we're going to estimate all depends on how accurate the device is. So let's say now, instead of volume, we're looking at a thermometer. Here's 50 and 51. And we can see that, unlike the previous page, now we've got all these graduations between 50 and 51. And so it'd be 50.1, 0.2, 0.3, 0.4, and this one, 50.5. So now we can see that the temperature in this thermometer, it's definitely higher than 50.4. But it's less than 50.5. So not only are we certain of the ones place, but because of the accuracy of our measuring device, we can say we're also certain of the 10th place. How do we record this? So it's 50.4, but we know it's more than 50.4, less than 50.5. So now, because our graduations, our markings on the thermometer show us every 10th of a degree, we estimate one digit further. So what are we going to show? We're going to show to the hundredths place. And we're going to now estimate, is it 50.45, 46, 47? And maybe we'll say here it's 50.47 degrees Celsius. But again, we're going to estimate one digit past our degree of certainty. And so for all measuring devices except for a balance, you take the number of decimal places that you can accurately read and you estimate one digit further. If you're using a digital balance, you just record all the digits. All right, so that's how we record our measurements. But this is also going to have an effect on any calculations that we do. So before we get into that, we need to learn and understand how to determine what we call our significant figures, or we often refer to it as sig figs. How do we determine those? So there's a couple of rules we need to remember. First rule, any non-zero, so 1, 2, 3, 4, 5, 6, 7, 8, 9, any non-zero, always significant. So if we have the number 132, there's 3 digits there, none of them are zeros, they're always significant. All 3 of them are significant. How about this number? Again, now 4 digits, none of them are zeros, so we have 4 sig figs. So what about zeros? Because if all non-zeros are always significant, then the only thing we have to worry about are zeros. Zeros, we'll see, fall under quite a number of different categories. So zeros between non-zeros, what do we mean by that? So 107 or 9.0342. These zeros are between non-zeros. And if they're between non-zeros, those zeros are significant. Zeros at the end of a number and, this and is important, to the right of the decimal point are also significant. So 1.00. That's going to be, we know the 1 is significant because it's not a 0, but these two zeros are also significant because they're at the end of the number and to the right of a decimal point. So that number is 3 sig figs. And that means that that number 1.00 is different from 1.000. This number is a more accurate measurement because it's been measured to 4 significant figures. All right, what we call leading zeros, not significant. What is a leading zero? So a lot of times you may just, if you had a decimal like 38 hundredths, you may have just written it like this. And typically we don't write it this way because having that 0 out in front of the number makes the number a little easier to look at. So if we call it 0.38, then there's no ambiguity that that decimal point is there. It's easier to look at. But this 0 is known as a leading 0. We don't have to have it there. And so the only significant figures in this number are the 3 and the 8. So this number has 2 significant figures. But those don't just have to be on the left side of the decimal point. This value here is 0.0038. All 3 of those zeros are leading zeros, and they're leading zeros because they're on the left side of the number. And so this number also would show as 2 significant figures. The final case is in many ways the toughest case because the final case is actually ambiguous. These are zeros at the end of the number but left of the decimal point. So for example, the number 1000. In the number 1000, we know the 1 is significant. But these zeros, it turns out, are ambiguous. So depending on whether one of these, 2, or all 3 zeros are significant, or none of them, the number 1000, the way we've written it, could have anywhere from 1 to 4 significant figures. How do we know? So there's a couple things we can do. One, if we want to be up at this end where all of the digits are significant, and this will look a little bit strange, but we could write it as 1000 decimal point. And that would tell us that all 3 of these zeros are significant. But what if we only had, 2 significant figures or 3? In that case, the best way to do it, the only way that's not ambiguous, is to use scientific notation. So for our number 1000 here, we can make it 1 times 10 to the third, 1.0 times 10 to the third, and so on. And now we use our rules that we learned previously, that zeros after the decimal point and at the end of a number are significant, we've now got 1 sig fig, 2, 3, and 4. So once we're able to identify the number of sig figs, what we need to be able to do is use them in calculations. And we'll talk about the rules for addition as well as the rules for multiplication. The one case where you can ignore is if you're using an exact value. So an exact value, for example, 1,000 milliliters in 1 liter, those are exact values. We know there's exactly 1,000 milliliters in a liter. We could write this like this. So when we're dealing with an exact value, we can treat that as if it has essentially an infinite number of significant figures. But for calculations, and this is why it matters, we can't have a calculated answer that shows more accuracy or more precision than our least accurate measurement. So the accuracy is controlled by the measurement that is the least accurate. Or in other words, the calculation from our sig figs will come from the least accurate one of those. So starting with addition and subtraction, say we're adding 17.63 plus 0.00111. And I haven't put any units on these, but it doesn't matter as long as the 2 units are the same. So let's add those. So if we just add them the way it looks, we're going to get 17.63111. Now, the accuracy of that answer matches the accuracy of our second number. But our first number was a lot less accurate. And so we're now showing a higher degree of accuracy than what we started with in this answer. So what we do, this first number has 2 decimal places measured. The second number, the last digit, is at 5 decimal places. So we're going to use the lower number of decimal places. So that's the top number, which has 2 decimal places. So that means we need to round our answer to 2 decimal places as well. Multiplication and division will give us some interesting results as well, if we are strictly thinking about significant figures. Because if I gave you this problem, hopefully most of you would give the correct answer of 21. But if we're taking sig figs into account, we would actually need to round that to 20. The reason that we do that is multiplication and division use the smallest number of sig figs. So 3 only has one sig fig, 7 has one sig fig. So that means our answer can only have one significant figure. So we'll do one more example here. We had 537 times 24. So if you want, you can go ahead and work through this as I do. And if I've done my math correctly, we get an answer of 12,888. But we then need to round. 24 here has two significant figures. 537 has 3. So the smaller number is 2. And that means that we need to round our answer to two significant figures, which in this case would give us 13,000. So from here, the next thing you should do is to get some practice in. There's a sheet labeled in-class practice exercise number 1. Go ahead and work on that. And the next video will be me going through the solutions to that exercise.